So bar charts, right? I do want to note the reason I want to talk about both here is because function visualization is really useful in pedagogical context in particular, or if you're modeling or you're kind of, in a very explicitly STEMmy field. But a lot of times you just want to visualize some actual discrete data that you've collected, whether that's through some instrument or through a survey or whatever it might be. Kind of the simplest way to go is a bar chart, right? For a bar chart, you just give it a list and it makes some bars. It's a big surprise, right? You can add colors just like before using color function, and you can add labels to each bar by using the option chart labels. Here I'm going to grab, say, the GDP of the countries from Latin America. Again, this is hand curated data. This is something Notebook Assistant has access to, but it's not LLM generated or hallucinated or pulled from the web. This is hand curated data. So here are all of the Latin American countries and their GDPs. We're going to format this as an entity association where each country is pointing to its GDP in this association. So it's kind of like a dictionary where we could look up Brazil and get the GDP, or Puerto Rico and get the GDP, whatever. And we can chart this data set with a fancy bar chart by just plugging it in here. We're going to add a color function. We're going to use log scaling because there are some pretty significant differences in these GDPs. And for chart labels, we're going to be a little bit fancy here. We're actually going to use a function. We're going to place automatic labels. They're going to come right from the association keys, the labels here. And we're going to put them on top, and we're going to rotate them by pi halves. So we're going to, instead of having them be horizontal, we're going to have them be vertical. We're going to add a frame, some grid lines, and we're going to make the grid lines dashed and gray and transparent, half transparent. And here we go. Here's our lovely bar chart here, which doesn't even fit on this monitor. Could make it a little bit smaller, but the labels will start to get a little bit crowded there, as you can see. But you can change the size of those labels if you like. But yeah, there's a nice bar chart. There's also pie chart if you want. Example data has a bunch of example data if you want to play around with this. Like you can look at these are all the different statistical data sets we have available, and you can read descriptions and column names and everything. These are all just there for you to mess with. But I'm going to keep using entities and entity properties because I think those are kind of more relatable in a sense. Okay, scatter plots. Oftentimes you don't have just one thing you want to visualize, like a bar chart, right? You want to visualize a relationship between two parameters. So we learned the other day that list is kind of how we represent, say, pairs of parameters. And so if you want to plot relationship between parameters, if you want to plot a list of things, the way you do that is by plotting a list and not by typing scatter plot, but by typing list plot. So the one-dimensional example basically just replicates bar chart, but with points, right? I'll show you a fancy function here. We learned about map. We have kind of the converse of map, the co-map. So I'm going to say list plot and bar chart, and both things will act on 1, 5, 10. So you can see here that these two things are effectively the same. It's just that this one uses bars and this one just puts a dot. And list plot will also work with associations and provide some nice data. So if we were to plot the GDP data here, and we can like mouse over and see that that's Brazil and that's Mexico, that's Uruguay, we can go through here and just see all these things. But if you want to use like a scatter plot, you're looking for a nested list because, a collection of pairs of paired up data, that's just a list where the elements are lists with length 2. So let me, create one here, kind of an interesting one instead of just some random numbers. So there's an actual relationship. I'm going to get a list, the elements of which look like this. And these are countries in Asia with their land areas and their populations. That's what the 2 data points are. And these things have units. Don't worry about the units. List plot will just work with the units without, causing any issues. And we can see here that we have the land area and the population related this way. And so it's pretty scattered. It's not one-to-one. You know, let's see if we can tease out something a little bit more. Let's say, oh, I preempt myself yet again. We can add scaling functions here. Say log. Now, I always use scaling functions because I like to use a function and then I like to modify its options. And this, you can see, is a much more instructive plot. The relationship is a lot clearer on a log plot. But just a quick note is that you can use things like list log plot or list log plot. The reason that these are separate functions is kind of historic. You know, back in the day, of course, when we had list plot, we were like, well, a lot of people in science want to do log scaling. So we should have list log plot and list log plot so that we can have the scaling. And then we thought, well, wouldn't it be nice if people could scale the axes in a bunch of different ways and not just be limited to like logs? And so we introduced the scaling functions option, and then we let you pick things like log or reverse or reciprocal or different, you know, custom scaling functions or whatever it might be. Here, I'm just adding a bunch of information. I'm putting in some tool tips. I'm changing the color function. I'm putting a frame labels, grid lines. Just like before, the point is really just to show you that you can get things looking how you want by adding in a bunch of different options here. And, you know, just to be very clear about this, list plot can be used to view any kind of 1 or 2 dimensional data. It doesn't have to be like socio-political or socioeconomic data or pulled from built-in data. So let me just create a noisy Gaussian where the coordinates are going to be x and then e to the minus x squared, you know, Gaussian form, and then plus a random number, also pulled from a Gaussian distribution. And what this looks like is it's a bunch of pairs, say -3 and 0.0011216, -2.95, just a bunch of pairs of numbers, right? And we can visualize that with list plot. And here you go. A useful thing to be able to do when you're talking about data visualization is that sometimes you want to show the data and maybe your model or some like ground truth on the same plot. If you want to combine visualizations with the same coordinate system, use show. And so we're going to show the list plot along with a plot of the original function that I used to generate the data without any noise, you know. So clearly this is not experimental, but maybe you can imagine this is experimental data and that the red line is your best fit model that you expect would have generated the data. You can see how they line up there just by using show to show the list plot and the plot together. And just like plot, list plot has a bunch of useful options. You can do filling, you can add plot legends, you can plot multiple data sets all together, just like this. And you'll notice that this looks startlingly like plot sine of x, right? And in fact, if we make the table be 2 coordinates, then these things look basically identical if we just set join to true. Again, you can also use, just like list log plot and list log plot, list line plot was another thing we made because people would like it. That's the same thing as setting joined to true. Just a quick note internally. Check out my plot here. This is the real plot of sine of x, right? It's not a discrete plot like list plot. It's the real plot of sine of x. I'll show you something scary. The full form of this thing, even this thing, is a Wolfram language expression like everything else you've seen. And basically what it is a bunch of options and then a list of points connected by lines. What's that list of points? It's this here. It's a big list of points. I'm going to pull that list out. You have a bunch of different rules here about how this stuff should look. You know, you don't have to care about any of this stuff. This is just kind of how the graph is set to be drawn by default. And now if I do a list plot of all those points that I pulled out, I'm going to iconize those points so we don't have to look at them. What do we get? Those are all the points that were used to draw the sign. And if we go and we do precisely this, what do we get? We get the beautiful sign function. So even when you're using plot internally, what's happening is that there are some complex calculations happening, as you can tell from the fact that it's not evenly spaced. We check the derivative of the functions you're using, and then at the derivatives, wherever the derivatives are large, and wherever we have endpoints, right? We draw more points, and then we just connect all the points with lines, and then we say, there's your nice continuous function, you know. So that's how that works. So here are some array plots. You know, in many cases, you don't have some set of pairs, but you have a collection of values, and those values have some spatial structure. This might seem kind of academic, like I say, but a matrix is an example of, say, a two-dimensional case where ostensibly the values could have some structure. Or really an image, you know, if you think about the pixels in an image, each pixel is syntactically, you know, contextually, same word there, basically. One is in Greek and one is in Latin. The pixels are related to the pixels around them, right? There's a spatial structure. And so if I make a table of sine of x, y, as x and y vary between negative pi and pi, steps of 0.1, and then I'm going to downsample it and round it so this is easier to see. But look at this. If you kind of zoom out, I wonder if I can make this smaller on this screen. Not without messing up the precision. Can I chop? I kind of suspect not. No. Well, on your own display, if you open this up, I think you'll see that there is actually a structure here. You can kind of see it even just looking at the numbers. But of course, that's not a really feasible way to visualize arrays, right? So there are a lot of different functions for that. Array plot is the basic no-nonsense approach. It just visualizes magnitudes by default. So here's your array plot. Matrix plot works similarly, but it gives you a little bit more chrome around the edges, and it will allow you to easily distinguish between negative and positive values, which is typically something you'd want, but sometimes it's not. Array plot and matrix plot both have a ton of options you can use. You can set, you know, again, custom color functions, built-in ones or ones you write yourself. Really, in the end, it's all the same. You can set specific color rules so that, like, wherever a 1 appears, it would be black or white or pink or whatever. You can set all sorts of things. You can get rid of the frame. You can add extra padding, remove the padding that exists. It's all good. Similarly, we had contour plot and density plot for surfaces above, and we have those for arrays just by putting list in front. So just like there's plot and list plot, there's contour plot and list contour plot. So here's that sign data. We made a contour plot. Here's the density plot of the sign data. Looks great if you ask me. And you can observe kind of the fact that, I mean, these things look beautiful, right? They look basically like I'm just doing it for the continuous function instead of discrete data. But you can observe how the discrete nature of these things vary by changing the step size. So say for matrix plot, and if you're working with topographic data in particular, relief plot can be pretty nice. So here we're going to visualize the terrain around Mount Everest. I say if you're working with explicitly topographic data is because this kind of casts a light down, and the light casts shadows that lets you see like the little bumpiness and everything really nicely. But it kind of exaggerates the differences in height so that you can see them better. It's like a topographic map where you can kind of run your fingers across the globe and you can feel, where the peaks and the valleys are. But the reality is that the Earth is, if you shrunk the Earth to the size of a marble, I think the comparison is that the peaks and valleys would be totally imperceptible to your fingers. I think they are literally like, something in my mind is telling me that it's like atomic size, but I think it might actually be, it might not be quite that small, but the Earth is very, very, very smooth. The topographic maps exaggerate, and so does relief plot. And here are, this gets all messed up on my smaller monitor here. Let me shrink. Just using CoMap again, just to point out that while these all visualize the same data, they look quite different. And so you got to pick the one that works best for your particular use. But you can see the differences here in the way these things are visualized. And of course, you can visualize this in 3D. So just like there's plot 3D, there's a list plot 3D. What do you know? There it is. And there's list plot 3D of the Everest elevation data. And instead of plotting like matrices where the entries correspond to heights, you can also plot triplets. So suppose you have triplets that look like XYZ, XYZ, XYZ. You can plot those too. You can also adjust the interpolation order when you're plotting these things. So you can see here, if I don't have super high resolution data, you can kind of see that it's just kind of drawing between the points and trying to guess what they look like. You can set that to be lower or lower still. It's a little hard to see because there's still a good amount of data here. But if you set it to 0, you can actually see these are all these are the actual data points that I have provided. And then it's interpolating between those whenever I use something like this. And on that note, if you do want to visualize points, you can use list point plot 3D, which I think is pretty neat. And then the last thing I want to talk about is geovisualization. So if you want to plot a list of geolocations, instead of list plot, you use geo list plot. So a lot of these functions you can find just by putting geo in front of a function that you know. So here's a plot of a bunch of different cities across the world. And it doesn't have to just be cities. It could be countries as well. That's fine. And when the countries are particularly small, like say Nicaragua or Albania here, they'll just be represented as little disks so that you can actually see them. Of course, you can change that, but that's the default. And geographic visualizations have full support for latitude and longitude lines and map projections, and everything is calculated such that it just works. So here's that plot from above, but what we're going to do is we're going to do a geo projection where we look at the bond projection, and we're going to put geo grid lines. So just like for a function, we had plot sine of x. You're sick of seeing plot sine of x, here you go. I'll switch it up for you. That's what that looks like, and you can set grid lines to automatic. Here, we set geo grid lines to automatic. And you can imagine that if instead of automatic, you put a specific list here, you could plot specific lines of latitude and longitude. But here we've got these geo grid lines, which are just lines of constant latitude and longitude with a typical spacing, and we have this geo projection here, bond, which changes the way things are displayed. You can also visualize two joined data sets for what it's worth. So here's like a list here. Just like you can plot two data sets with list plot, you can plot two data sets with geo list plot. And so here's, kind of a path between one set of countries and another set of countries that we got by putting joined to true. So geo bubble chart and geo region value plot are your options for visualizing values that are associated with geographic locations. Basically, all the other functions here that you see, they all share options. So they all can use geo grid lines and geo projection and geo range and all this stuff. And there are dozens and dozens and dozens of map projections. So here, for example, is the GDP of the countries, or the GDPs of the countries in Asia, using an orthographic projection with automatic grid lines and with watermelon colors, one of the built-in functions. You can pick whatever you like. And so there they are. You can look at, say, with Geo Bubble Chart, you can draw bubbles that are also colored here. And what this is the size of the bubble will indicate the border length, is what I picked to take a look here. So what is the length of the border? And I want to note, we've been looking at scalar values, but GeoVector is a real function where you can plot vectors on a geographic visualization. So what I've done is I've made 100 randomly geopositioned vectors across the entire world. That is a real function, random geoposition, whole world, give me 100 random geopositions. And then I make a table of geovectors with bearing 10, which is north. And so here are 100 different random geovectors in the Mercator projection, in the equirectangular projection, in the Mulfida projection. You can see the different projections have different properties, right? So here we have these rectangular layouts of the latitude and longitude lines. And here we have curved ones. And the difference between these two is that this is what is the term? Is it conformal? Is it equiangular? I forget. These ones preserve angles. So if you're pointing north, north looks the same everywhere. But what the cost for that, the trade-off, is that you totally distort the areas. Like, I think most of us are familiar with the fact that the Mercator map has very distorted areas. Like, it makes, say, Latin America and Africa look much smaller than they actually are, and it makes Greenland look massive, Russia looks super massive. It's already pretty dang big. And then Antarctica is, destroying the world down here. It's so big. But that's just not really true. So if you're willing to give up the absolutely correct angles, in a sense, you can get correct areas by switching to a different map projection like this. So this doesn't have, all these things are pointing north still, but they don't all point up like they did before. The difference is that now all of the areas are relatively correct here. So this has the correct size of, say, Africa compared to South America, or North America compared to Australia, or Antarctica compared to everything else. And this is just to note, we have a bunch of different map projections, even crazy ones like the Pierce quincunxal projection. One of my favorite map projections for simply how bonkers it is. I also think it looks really cool. But you can see, really the important thing is that the geogrid lines and the vectors that we drew, and honestly, any shapes that we drew, any polygons that we drew, whether they're countries or just like if we picked out a patch, these things, they just automatically work with whatever map projection we want. And that's kind of the magic. So really the point of this whole lecture is just that whatever kind of visualization you want to make, or whether you're starting from a function or data, whatever kind of function, Wolfram Language has you covered. You can make anything. There are a lot of good examples in our courses. I think if you're math or physics minded, the multivariable calculus course has some really incredible visualizations that I really would have liked to have when I was learning multivariable calculus. But that is that.